All right, good afternoon. My name is Hunter, and this is week 5 for Gen Chem 221. We're looking at stoichiometry and limiting reactants. So stoichiometry, and specifically this technique of dimensional analysis, is probably the thing that I use most in my everyday when I'm not doing chemistry in school. So this is a really good thing to practice and get familiar with. I'll try and identify some strategies for approaching these problems to make them a little bit easier if you're not sure where to start. So we're still in chapter 4. We're just going to be doing a handful of questions to get some additional practice here. So to kick things off, number 44, write the balanced equation, then outline the steps necessary to determine the information requested in each of the following. We're going to look at D. And 44D here is the number of moles, find the number of moles and the mass of water formed by the combustion of 20 kilograms of acetylene, or C2H2, in an excess of oxygen. So we're given some really important information here. And so I'm going to use my highlighter here. We need to determine the number of moles, and mass. That's what we're trying to get to, of water specifically. When you're not sure how to approach these problems, I found it really helpful to, off in the margins here, write down, let's see, basically write down everything that we're given and everything that we're trying to get to. So we're trying to find moles of H2O, and we're trying to find mass of H2O formed by the combustion of a mass of acetylene. So the mass of C2H2 that we're given is 20 kilograms. Zoom out here just a little bit, give ourselves more room to work with. So we don't use kilograms a whole lot when we're dealing with atomic mass, so I'm going to go ahead and just convert that to grams so that we have it. We just multiply by 1,000. And we'll do this long form here in a second. And then we're going to have to look up, let's see, eventually we're going to have to look up the exact atomic mass of C2H2. So we'll get to that in a second. First, we need to write the balanced equation. So in a combustion reaction, basically you're reacting whatever your reactant is with oxygen, an excess of oxygen. And we are producing CO2 as a byproduct and H2O. So this is our starting point. First thing we got to do is balance this. So, like we did last week, we can just go down the line and count how many of each thing we have on the left and on the right. Let's keep it in order, just to keep it simple. We have 1, 2, and 3. So this is going to be our first hurdle. The minimum common multiple of 2 and 3 is 6. So let's go ahead and get there. Gives us 1, 2, 3, 4, 5, 6. Yeah, so 2 times 2 is 4, 2 times 1. Just to make that super explicit. So we've got our oxygens balanced, but now we've changed our number of carbons and our number of hydrogens. Am I missing something here? CO2 and H2O. Yeah, there's a much more simple way to do this. Okay, sometimes you just got to work it through. So, same thing, count what we got. One carbon. We've got two hydrogens, three oxygens. We can simplify this even further. So if I take, let's do, yeah, let's start with doubling these. Gives us four carbons. That gives us 8, 9. So we're not quite there. That would give us 10. And 4 there. That's what we needed. So now we've just got our oxygens, and we can simply multiply that by 5, and that gets us to 10 total. And now we're balanced. Okay. So we've got our balanced equation. We know what these reactants and products are in relation to each other, and now we can start to solve for the moles and the mass of water that will be formed. So this again is a combustion. Sometimes you'll see a triangle under the reaction arrow here to show that this is the addition of heat. So this is a combustion reaction of a hydrocarbon is always going to produce CO2 and water as byproducts. So we're given a starting mass of our reactant, our starting mass of acetylene. So looking at our periodic table, we pull that up. Our mass of carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. Grab your scientific calculator. So the quantity 2 times 12.01 plus 2 times 1.01 gives us a mass of 26.04 grams per mole of acetylene. I keep writing it backwards. I'm not sure why. Okay, so we have grams per mole. Now we're given 20 kilograms of acetylene as our starting mass. So we can figure out what these multipliers here in our balanced equation tells us the ratio. So for every 2 moles of acetylene, we're going to produce 2 moles of water. Because that's 1 to 1, this kind of simplifies our math a little bit. I'll see if I can show that. So we have 20,000 grams of acetylene. Every mole of acetylene has 26.04 grams. This is that setup. Having grams of acetylene as our units on the top left, and grams of acetylene on our bottom right. Those cancel out, and so we do 20,000 divided by 26.04 gives us 768.05 moles, because our top right now is our units that we're keeping, moles of acetylene. Now again, for every 2 moles of acetylene, we produce 2 moles of water. And so we're going to produce exactly the same number of moles of water because there's a 1-to-1 ratio of acetylene to water. All right, so we've got part of our problem answered. Now we need to find the mass of water. To do that, we've got our handy table again. Hydrogen is 1.01 grams per mole. Oxygen, 15.9916 grams per mole, depending on what source you're using. So we've got the quantity, 2 times 1.01 plus 16 gives you 18.02 grams per mole of H2O. We're most of the way there. We have a grams per mole, and we have a number of moles. Now we just multiply those to get our final answer. So I'm running out of space here. We have 768.05 moles of H2O. And for every mole of H2O, we get a mass of 18.02 grams. Moles cancel out, and we simply multiply 768, let me get this, 768.05 times 18.02 gives us 13,840.26 grams is the unit of measure that we're keeping. This is a pretty large number. So to keep this simple, we can simply do our conversion from grams to kilograms. So divide that number by 1,000, and that gives you 13.84 kilograms of H2O will be produced. And that is your final answer. Find the number of moles and the mass of water formed. Yeah. All right. Question 47. So gallium chloride is formed by the reaction of 2.6 liters of a 1.44 molar solution of hydrogen chloride according to the following equation. We're given this balanced equation. How nice of them. So we don't have to balance it this time. Outline the steps necessary to determine the number of moles and mass of gallium chloride. Perform the calculations as outlined. So this is one, again, where we're given a lot of different numbers, and it's helpful for me, at least, to take a look at what we're given. We were given this volume of 2.6 liters of gallium chloride. Or excuse me. We're given 2.6 liters of a hydrogen chloride. Solution. And we're told that the molarity of hydrogen chloride is 1.44 molar. Remember that molar is moles per liter. So that is what's going to get us to the number of moles. To find the mass, we then just need to know the molecular mass of gallium chloride, which we can calculate looking at our periodic table. Determine the number of moles and mass of gallium chloride. So all we're given is a balanced equation and a volume and a molarity of the reactants, and we need to figure out the products. Okay. So we're given reactants, we need to find products. So let's start with figuring out we're given a 6:2 ratio here. So 6 moles of hydrogen chloride per 2 moles of gallium chloride. That might simplify things for us a little bit. So let's see here. We're trying to get to moles and mass of gallium chloride. Okay. So we're given 2.6 liters of HCl. For every liter, we get 1.44 moles of HCl. Those will cancel out. For every 6 moles of HCl, we produce 2 moles of gallium chloride. That is going to get us our moles of gallium chloride. Because notice, I'm going to do this in a different color. Liters of hydrogen chloride will cancel out. Liters of hydrogen chloride. Moles of hydrogen chloride. Moles of hydrogen chloride. And our final unit will be moles of gallium chloride. And you can do this in one step on your calculator. So 2.6 times 1.44 times 2 divided by 6 equals 1.248 moles. And that's more significant figures than we're allowed because we're dealing with significant figures here. Moles of gallium chloride. I want to be thorough, so I'm going to check my answer key here. 47. All right, we're on the right track. So 1.25 moles of gallium chloride. We're halfway there. We need to find a mass. So we have gallium, chloride. There's going to be 3 of those. Check our periodic table. Gallium has an atomic mass of 69.7 grams per mole, while chlorine has a mass of 35.45 grams per mole. Add those up, we've got 69.7 plus the quantity 3 times 35.45 gives us a molecular mass of 176.05 grams per mole for gallium chloride. We have 1.25 moles of gallium chloride and a mass of 176.05 grams per mole. Gives us our final answer of 220.06 grams of gallium chloride. Checking my answer. I left too many significant figures on there. So a more precise answer would be 2.2 times 10 to the 2 grams of gallium chloride. Cool. Moving on. What volume of a 0.2089 molar that potassium iodide solution contains enough potassium iodide to react exactly with I think that's copper nitrate in 43.88 milliliters of a 0.3842 molar solution of copper nitrate. I don't want to lead you all astray, so I'm going to find out if that actually. Yes, more specifically, that is copper 2 nitrate. Fantastic. Okay. So the language here containing enough suggests that this is a limiting reactant problem. And we can infer from this language that potassium iodide at Ki is going to be our limiting reactant. So we know, or we can guess, that we have an excess of copper nitrate. And looking at our balanced equation, which they were so nice to provide for us, for every 2 moles of copper nitrate, we need 4 moles of potassium iodide. So if you were given the 2 identical masses, that would make sense. But we're not given masses, we're given molar solutions. All right. We're given a concentration, we're given a volume, and we're given another concentration. What volume? Okay. Let's see here. We're given concentration. To react exactly with a volume. Copper nitrate. Moles per liter. Okay. Starting with concentration, get to volume. Okay. Let's do how do I want to do this? We're going to start with our concentration of copper nitrate and see how this works out. So we're given 0.3842 moles per liter of copper nitrate. Let's see. The brain ain't braining today, y'all. Must be Friday. Yeah, okay, we're almost there. Let's start with our volume of copper nitrate. We're going to go ahead and convert that into liters, because we're dealing with units of molar. And we know that we're given a concentration, there it is, 0.3842 moles per 1 liter. Okay, that is going to get us to our moles of copper nitrate. Okay, from there, well, let's get that far. 43.88 milliliters divided by 1,000 times 0.3842 moles per liter gives us 0.01686 moles of copper nitrate. I want to be a little bit more tidy here. So 0.01686 moles of copper nitrate. From there, we know that for every 2 moles of copper nitrate, looking at our balanced equation, we need 4 moles of potassium iodide. We're also given a concentration. We can go ahead and plug that in, save ourselves a step. Moles of potassium iodide per 1 liter of potassium iodide should give us the volume of potassium iodide we need. So we take our 0.01686 moles of copper nitrate times 4 divided by 2 divided by 0.2089 moles of potassium iodide gives us 0.1614, cancel out our units, liters of potassium iodide. And since we started in milliliters, we can go ahead and multiply that by 1,000, gives us our 161.4 milliliters of potassium iodide. Cool. Oh no. Thank you for drawing my attention to the chat. Let's see. Unfortunately, I don't have a great way of moving that, but I can move the screen around so that hopefully you can see a little bit better. All right, moving on to 61. I'll try and keep it centered this time. What is the limiting reactant in a reaction that produces sodium chloride from 8 grams of sodium and 8 grams of diatomic chlorine? So they were kind enough to give us a starting point for our balanced chemical equation here, but we're given masses, which at the moment doesn't seem super helpful, but we'll get there. All right. So first things first, let's balance our equation. Diatomic means there's 2 chlorines on that left side of the equation, so we have to double this. The only other thing we have to worry about is that sodium. So really, really easy balancing of this equation. Won't go too much further into that. So what is our limiting reactant? we know that we have 8 grams of sodium and 8 grams of chlorine. It's not enough to look at this and say that they're the same. We got to look at those molar mass, those atomic masses. So 8 grams of sodium we're going to find, I'm basically setting this up without even looking at the values because we can. Once we have that molar mass, we can do our conversion. Let's see. What is the limiting reactant? For every 2 moles of sodium, there's 2 moles sodium chloride. So that's a 1-to-1 relationship. And then based on what that gives us, we'll be able to determine if this is our limiting reactant. So the mass of sodium is 22.99 grams per mole. So we take 8 divided by 22.99 times 2 divided by 2 would be 1. So straight across, we can just ignore that. Gives us 0.34797. So we'll go 8. 0.348 moles of NaCl. Now we do the same thing with our diatomic chlorine. And diatomic chlorine, so you take the molar mass of chlorine and multiply it by 2, that would give us 70.906 grams. And our relationship is a little bit different for moles of product to moles of chlorine reactant. It's 2-to-1. So we take 8 divided by 70.906 times 2 gives us 0.226. 0.226 moles of NaCl. Now, because that resulted in a smaller number of moles, we can say that that is our limiting reactant because that amount of chlorine can only produce 0.226 moles of sodium chloride as opposed to 0.348. So chlorine in this case is our limiting reactant. Okay. In a laboratory experiment, the reaction of 3 moles of hydrogen, diatomic hydrogen, with 2 moles of iodine, diatomic iodine, produced 1 mole of hydrogen iodide. Determine the theoretical yield in grams and the percent yield for this reaction. So far, so good? Okay. Determine the theoretical yield in grams and the percent yield for this reaction. We're given 3 moles of hydrogen. Monatomic hydrogen would be 1.01, so 2.02 grams per mole of hydrogen. times 3 gives us 6.06 grams of hydrogen. Oh, we can even cut out a few more steps here. Yeah. Yeah, let's do that. Okay. Well, we've done it, so let's leave it. For every, well, let's play this out. We probably don't need this information, but it's good practice. So 2 moles. We've got 126.9 times 2 gives us 253.8 grams for diatomic iodine. Good practice. We don't really need this information. What we do need is the stoichiometric relationship. So we were on the right track with moles of hydrogen, but what we need is the relationship of moles of hydrogen to moles of hydrogen iodide. And for that relationship, we had 2 to 1. Then we need to know our molecular mass of hydrogen iodide, which is, what was it, 126.9? 126.9 plus 1.01 gives us 127.91. Okay, 127.9 grams per mole of hydrogen iodide. I hope this is making sense. So let's run that. 3 moles times 2 divided by 1 times 127.9 gives us 767.4 grams of hydrogen iodide. We're not done. We have to figure out which of these reactants is the limiting reactant. So let's check out our iodine. So for every mole of iodine, we get 2 moles of hydrogen iodide. Do the same thing. 2 times 2 times 127.9 gives us 511.6 grams of hydrogen iodide. 511.6 grams is less than 767, so we know that iodine is our limiting reactant. And that our theoretical yield is 511.6 grams of hydrogen iodide. What is our percent yield for this reaction? Well, let's take a look. So percent yield, this is a good formula to have memorized. Is actual yield divided by your theoretical yield. let's see here. In a laboratory experiment, the reaction of 3 moles of hydrogen with 2 moles of iodine produced 1 mole of hydrogen iodide. So our theoretical yield is 511.6 grams, but how many moles is that? That would be 127.9. That's the wrong way to do this. Let me think for a second. Ah, okay. So the actual yield was only 1 mole. Yes. And we know that each mole of hydrogen iodide is 127.9 grams. So that was our actual yield. So our actual yield was 127.9 over the theoretical yield of 511.6 gives us 0.25, and to get a percentage, that is 25%. So your theoretical yield was 511.6 grams, or 4 moles of hydrogen iodide, and yes, 4 moles of hydrogen iodide. Your percent yield was your actual yield divided by your theoretical yield was 25%. So the reaction was 25% what it could have been. All right, that is all the practice I have for today. Recordings will be up on the Portland State University Learning Center YouTube channel shortly. You can always find recordings of previous streams there. Don't hesitate to reach out if you have any questions. I hope this was helpful.